about our next topic of kinematics, which is free fall motion. And free fall motion is really about vertical motion. And what I want to do here is that I want to really talk about, what this word even means here, free fall. What we find here is that when we say the word free, we mean no air resistance. And the word fall really means here is that Earth's gravity causes objects to fall. And the one thing that we got to be careful here is that a lot of times people will say, oh yeah, they're in free fall. If a skydiver is in free fall, it is dangerous in the world of physics because there's no air resistance. So you just keep accelerating. You're going to hit that ground. It's going to be ugly. There's no doubt about it. And what you find here is that what do we know about free fall motion? What we know about this is this. Objects in free fall always have the same acceleration. They always have the same acceleration. And what's pretty amazing is that you could take a little person, maybe a little baby, right? You could think about a baby, or you could take a very large sumo wrestler, and you take them and you drop them. And if you were to drop them in free fall, these guys would have exactly the same acceleration. It's independent of mass, okay? These guys are independent of mass. Why are they independent of mass? We have to wait till Newton's second law to really answer this question. But they always have the same acceleration, no matter what. And so the question is that this acceleration that we're talking about is known as the acceleration due to gravity. And what we know here is this here, that since acceleration is a vector, we need two things, direction and magnitude. So you got to be careful here, okay? You got to be careful here. There are people that are going to screw this up that's going to haunt them for the next 3 months. So what do we mean by that? Well, for starters here, we want to think about the Earth. So you could imagine that we have our pale blue dot, right? Carl Sagan statement. And when you look at the acceleration due to gravity, what you're going to find here is that the acceleration of gravity always points to the center of the Earth. Always. So when you're looking at this thing, no matter where you're at on the Earth, you're feeling this acceleration here. And as an abbreviation, I'm going to call that the acceleration due to gravity. Now, here's the issue here, and you got to be really careful. We define our directions here. It's customary to go upward as positive. So upwards has a positive sign. And then downwards, negative, downwards has a negative sign. Okay, so here is probably the most important thing. And like I said last time, it haunts some people the whole semester. And as the semester goes on, I get less and less forgiving and I start taking more and more and more points off. So you got to be careful here. So here we go. Here's our definition. Okay, our definition is that the acceleration due to gravity has what? It's defined as AG. Now remember, there's two pieces to acceleration, right? It has direction. What is the direction of acceleration? It is negative. The acceleration, that negative sign is the direction. And a lot of the times you don't put in a minus sign. If you already know the direction, then it's typically the magnitude that you're focusing on. So what's the magnitude? The magnitude is called little g. So when you look at this value here, it's really what? It's minus 9.81 meters per second over 1 second. But many times, due to sloppiness, we write it as 9.81 meters per second squared. And when I say sloppiness, I mean including myself. And so that's the magnitude right there. And people will just keep using that minus sign, even though there's already a minus sign, and they give double minus signs to themselves. And I'm not kidding. For 25 years or 24 years, I've seen this being plagued by numerous people. Okay, so let's check this out. What does this 9.81 meters per second squared mean? What it is here is that it's an average. The value of g being 9.81 meters per second squared is an average value. When close to the surface of the earth. And it's actually a value, pretty far up away from the earth. So what I mean by this here, you may have heard of the guy that jumped from the edge of the atmosphere. So when you're looking at this picture here, what you can imagine here is that here's the earth. And so when we're thinking about the earth here, what we're seeing here is the following thing here. We know that from here to here is the radius. And when you look at the radius, I don't really know what the radius is, but it's somewhere between 6,000 to 7,000 kilometers. So it's probably about 6,000 to 7,000 kilometers, somewhere in that ballpark. Let's say 650. And you probably heard about the jumper that jumped from 140,000 feet, right? I think it was 100. It's over 100,000. So when you get to the top of the atmosphere, okay, this is top of atmosphere. That distance between the top of the atmosphere, okay, let me draw this a little bit better. That distance from here to here, I know it's 40 kilometers. I'm kind of guessing, I think it's about 140,000 feet. So just think about this here. So so when that jumper did, what you'll find here is that if you look at the ratio of 40 kilometers, which is the top, versus let's say the average of these, well, you could see that this ratio is tiny, right? This is about 4 in 650, which is much less than 1. So when you go to the surface of the Earth, this is 9.81. When you go up about 100,000 feet, I bet it's about 9.80. It changes right? It's 2 within 100th. And you can see that's about 100. So the acceleration due to gravity is pretty constant, even as you go up to the top of the atmosphere. Another thing that I think is really interesting is that I let me be careful. I think it was in the 1980s they released, and what I mean by released, that means the military. They released the data for the variations on G. And you might say, like, well, what the hell do you mean by that? Well, let's imagine that you look at the surface of the Earth. Okay, so here's my pale blue dot again, right? What you find here is that you can have caverns, right? So what you get here is that you'll get a low density, and then you can have regions that have a high density. So then in this case, you have a high density. So you could imagine that you have a green country that's angry at the red country over here. And what do? They decide to send them a little care package. So you're seeing this little care package that's moving through. And as you send this little care package, what it does here is this. These variations will alter the trajectory of the care package. And so by knowing these densities, these variations, you'll find that if you're not careful and you don't know these, you'll never hit the red country with the care package. So it's a big deal, actually. And I was shocked when they released that, because I didn't think that was a big deal until I learned a little bit more about it. And then it makes sense after a while. So that's all about the acceleration due to gravity. So remember, what's the most important thing? The acceleration due to gravity has two things. It has a sign and it has a magnitude. Don't keep putting in double minus signs. That's super, super important. Okay, let's get a feel for this, just to show you that what we've been talking about in the past is very similar to what we're doing here. So for a brief moment, let's round G to 1 sig fig. So that means 9.81 becomes 10 meters per second every 1 second. Okay? Remember, just to be careful, these are for calculations. This is for guesses. Never use 10 meters per second every 1 second. This is only a conceptual thing. So here we go. So what happens if you drop a ball? Well, if you drop a ball from rest, what we do know is that that object is going to start to do what? It's going to start to speed up. The question is, how does this thing speed up? Well, if this starts off at 0 seconds and it goes to 1, 2, 3 seconds, and I have an acceleration of g equals to 10 meters per second every 1 second, you could see here is that if I start off at a speed of 0, when I get to 1 second, it has to change by 10 meters per second. When I get to 2 seconds, it's got to change by 20 meters a second. When it comes to 3 seconds, it's got to change to this. Now note, I did not put any signs in here. So these are the speeds. If I want to put in my velocities, then I got to come in by hand and I got to put a minus sign here. So the minus sign tells us about the direction. It's going down because our direction is, that's negative, up is positive. So in this case, if I write because the fact that I have an arrow, that means it automatically implies a minus sign. But if I want the acceleration due to gravity, then I write this here. What happens if I'm throwing, let's say that I do something slightly different. Let's say that I take a glob of something, I don't know. Here's my glob. And now what I'm going to do here is that I'm going to throw this at what? 30 meters a second. Maybe it's negative 30 meters a second. What's going to happen? The fact that I have acceleration due to gravity going in that direction, I know it's going to speed it up in the negative direction. So that means at the next moment, what's it doing? It's going faster. How much is it going faster by? Well, in this case, it has to increase it. So it now goes to 40 meters a second. So it doesn't matter. The acceleration due to gravity is a constant value here. So let's go look at things. So what you're seeing here is that because we now know the acceleration due to gravity, in problem solving, the only thing that changes in data tables is that you now know the acceleration due to gravity. So if I come over here and I start to write this, this guy now is a known quantity. I can come in here and I can write, I know what that acceleration is all the time. And it would seem that if you're given this extra information, that problems become easier. Caution. Problems might actually become more challenging because textbooks have a tendency to write these things a little bit more challenging because they're saying, hey, you got this extra piece. We're going to make you think a little bit more here. So you gotta your spider senses has to be going off here, okay? You gotta make sure that you understand what we're talking about here. Okay, let's go. So the next thing that I want to go do here is that I want to go in and I want to try to do try to grasp conceptually what's going on. Okay, so here we go. So what we want to do is that to conceptualize the motion more, so I want to of a thrown ball. So here we go. So the first thing that we want to do here is that we imagine that if I throw a ball up, what does that mean? That means that I'm throwing the ball up at some initial speed here. So if I'm throwing a ball up, you could imagine that at 0 seconds, my hand is going and then I release the ball at 0 seconds. So I had time to accelerate with my hand, but that's not free fall if I include my hand here. So what we assume here is that when this thing is thrown up, let's say that because this is my positive direction, this is my negative, you can see that the speed here or velocity is in the positive direction. So what I'm assuming here is that this thing is leaving from the ground, right? So this is leaving from y equal to 0. So what happens then? Well, because we have acceleration due to gravity, okay? So acceleration due to gravity, look how I'm writing, g. I know that this guy is going to decrease. It's going to decrease, and then at some point it's going to do what? I've run out of space. Let me move this down just one square. We see here at this point here that it stops. And then what does it do after it stops? It turns around. So when you're looking at this, we could see here is that this guy's going to go after 30. It's going to go what? It's going to go 20, 10, and then at the very top, the speed is 0. So it decelerates. And then what you're going to find here is that because the acceleration is constant at equal time intervals, what you're going to find here is that let's count the seconds here. That's 0, that's 1, that's 2, that's 3. This is 3. And then look what happens. This is 4, this is 5, and then this is 6. So when I look at the return fall, look what actually happens now. You're seeing that there's no arrow at 3 seconds because it's at rest. But now it goes from what? From 0, and in 1 second it's going what? 10 meters a second. So you know what? I got to move these times over to the other side. I need the space. And so what you're seeing here is that this is 10 meters per second, but remember the direction. How do I tell the speed of 10 meters per second when it's going up or down? I can't. Speed doesn't have direction. How do I tell the difference in velocity? By my sign. And so you could see that from 0 to 1 second afterwards, 4 seconds, 3 to 4 seconds, it's now moving 10. And so then it's moving what? It's moving 20. So when it comes back to the ground, right before it hits the ground, it's moving 30 meters a second. So what you're seeing here is that you have symmetry, right? You have symmetry. And what I mean here, let's make some remarks here just to summarize this thing. The first thing that you should see here is that there's symmetry in time and space. Or not time and space, but time and speed. You're going to see that the time up, which is what? 1, 2, 3, 3 seconds is equal to the time down, which you got 3, 4, 5, 6, which is another 3 seconds. So you get the same time up as down. And what you find here with the speed here is that you have the speed, you have equal speeds at equal speeds at, I don't want to say equal time intervals at, I'm going to say equal time intervals. No, at certain time intervals. There's probably a better way to say that. And what I really mean here is that you could see that from 3 seconds to 2 seconds, that's 1 second. And when you look at that, you could see that we have the same speeds. And here's another one here. The acceleration is always constant. What do I mean by that? Well, constant means the following thing here. That means that even at the top, where v is equal to 0, the acceleration is not equal to 0. It's equal to what? Minus g. And if you think that because something comes to rest momentarily, that the velocity or the acceleration is 0, it is not 0. So you want to pay attention to that, okay? So the question is that, is it equal heights? Well, it could be equal heights for the, these time intervals. Equal heights from what? From the ground? I guess if they're, yeah, I think I agree with you. At equal height. Okay. Thanks, Natalie.